Hi everyone, my name is Daniel Loureiro. I'm a PhD student at University of Porto and I'm here to present MedLinker, which is a medical entity linking solution combining neural representations and dictionary matching. As everyone knows, the medical literature is vast and keeps growing rapidly. Everyone also knows, perhaps now more than ever, that the information in these works is extremely valuable. Unfortunately, it's also very hard to parse. The current state-of-the-art of natural language processing has made great strides and can be especially helpful for entity linking in this domain. However, we'll see that the purely neural approach is insufficient and a better solution can be achieved combining it with other methods such as approximate dictionary matching. So let's start by defining our task. Given an abstract, such as this one, we need to first recognize relevant spans which may mention entities, and then match each span to a concept from a medical ontology. Now, this presents us with the first challenge. The medical ontology of interest to us is UMLS, which is very comprehensive, but it includes a very large number of concepts, over 3 million compiled from multiple sources. Additionally, we'll be working with the MedMentions corpus, which has the most UMLS annotations, but still presents very low coverage of UMLS, covering only about 1% of all concepts. The low coverage also becomes a problem across the dataset splits, with almost half the concepts in the test set not occurring in the training set. Looking at the method now, we first need to recognize the relevant spans. To achieve this, we make use of a standard named entity recognition architecture, a BILSTM with a conditional random field layer, and we initialize this model with contextual embeddings from a state-of-the-art neural language model trained on the medical domain. Note that we're not training this NER solution for linking. The only labels to predict here are whether a span is relevant or not. Moving on to our matching methods. Here, focusing on contextual embeddings, we employ the same language model used for span recognition, but now to train a classifier that predicts concept labels from contextual embeddings. Since our training dataset provides us with called spans, we don't require predicted spans during this step. Based on our previous work on word sensitive equation, we use a pooling procedure combining information from different layers of the NLM to represent our contextual embeddings. We also experimented with using nearest neighbors, but found that a lightweight softmax classifier worked better. During testing, we must predict spans first, so it involves 3 steps. We make 2 passes through the LNM, first to predict spans for a sentence, and then to obtain pooled contextual embeddings corresponding to those spans. And finally, we classify those contextual embeddings to obtain our entity matches. Our other matching method explores character Ngrams. We take advantage of the fact that UMLS provides a large set of alternative names for every concept. Using SimString, we break words into fixed-size character Ngrams, trigrams in particular, that can be used for approximate dictionary matching. So for instance, the concept for this syndrome has 4 name variations. The trigrams for each of these names constitute features for that concept. These features can then be matched using cosine similarity against query strings by their corresponding trigrams. We match query strings against all names individually. The entity whose name had the maximum score corresponds to our best match. We've covered our matching methods, now we need to discuss how we combine them for our final predictions. After some testing, we found that taking the maximum of both matches was a good predictor. The reasoning behind this is that string matching scores should be higher in most cases than the class probabilities, effectively making it the default matcher except when the trigram overlap is very low or null, in which case the classifier probabilities take over. Still, we found that this approach allowed for too many false positives, which may be especially harmful in this domain. So we optimized for precision by training a logistic regression classifier on an assortment of score variations and learned the optimal threshold for more balanced performance. We performed this optimization both for linking concepts and types for comparison with other works, as we'll see in a moment. To summarize, here's our full pipeline. Given a sentence for processing, we first apply NER to recognize the relevant spans. Then, those spans are matched independently using dictionary and contextual methods, followed by a post-processing step that combines individual predictions from both into our final predictions. We evaluated our work on the test set of med mentions for both concept linking and type linking. There are few prior works using med mentions, so we also report additional results using popular solutions, namely Quick UMLS and SciSpaCy. Let's first look into our type linking results. Of the two linking tasks, this is the most simple as there are only 21 possible type labels. Our final scoring method performs similarly to the prior work of Nejat Ghali, which essentially employed the NER solution we've described for both span recognition and linking. Our solution, however, is primarily designed for concept linking, where we expect to match millions of labels, which is unsuitable for the NER approach by itself, so we're glad to see that it nevertheless performs well on type linking too. Now looking at the concept linking results, which are our main results, we see that we outperform the prior reported system, Tiger1, by a considerable margin, as well as the other additional baselines. Note that in both tasks, we see very significant improvement from the combination of string matching and the contextual classifier. In conclusion, we've seen that medical entity linking is still very much a challenging task and that we require new approaches that make up for the lack of annotations, and we've also seen how neural language models can be effectively combined with dictionary matching using lightweight methods. You can find the code available at GitHub, and thanks for watching.